In mathematics, non-Euclidean geometry consists of two geometries based on axioms closely related to those specifying Euclidean geometry. As Euclidean geometry lies at the intersection of metric geometry and affine geometry, non-Euclidean geometry arises when either the metric requirement is relaxed, or the parallel postulate is replaced with an alternative one. In the latter case, one obtains hyperbolic geometry and elliptic geometry, the traditional non-Euclidean geometries. When the metric requirement is relaxed, then there are affine planes associated with the planar algebras which give rise to kinematic geometries that have also been called non-Euclidean geometry. The essential difference between the metric geometries is the nature of parallel lines. Euclid's fifth postulate, the parallel postulate, is equivalent to Playfair's postulate, which states that, within a two-dimensional plane, for any given line and a point A, which is not on, there is exactly one line through A that does not intersect. In hyperbolic geometry, by contrast, there are infinitely many lines through A not intersecting, while in elliptic geometry, any line through A intersects. Another way to describe the differences between these geometries is to consider two straight lines indefinitely extended in a two-dimensional plane, that are both perpendicular to a third line. In Euclidean geometry, the lines remain at a constant distance from each other and are known as parallels. In hyperbolic geometry, they curve away from each other, increasing in distance as one moves further from the points of intersection with the common perpendicular. These lines are often called ultraparallels. In elliptic geometry, the lines curve toward each other and intersect. History. Early history. While Euclidean geometry, named after the Greek mathematician Euclid, includes some of the oldest known mathematics, non-Euclidean geometries were not widely accepted as legitimate until the 19th century. The debate that eventually led to the discovery of the non-Euclidean geometries began almost as soon as Euclid's work Elements was written. In the Elements, Euclid began with a limited number of assumptions and sought to prove all the other results in the work. The most notorious of the postulates is often referred to as Euclid's fifth postulate, or simply the parallel postulate, which in Euclid's original formulation is: if a straight line falls on two straight lines in such a manner that the interior angles on the same side are together less than two right angles, then the straight lines, if produced indefinitely, meet on that side on which are the angles less than the two right angles. Other mathematicians have devised simpler forms of this property. Regardless of the form of the postulate, however, it consistently appears to be more complicated than Euclid's other postulates. 1. To draw a straight line from any point to any point. 2. To extend a finite straight line continuously in a straight line. 3. To describe a circle with any center and distance, radius. 4. That all right angles are equal to one another. For at least 1,000 years, geometers were troubled by the disparate complexity of the fifth postulate, and believed it could be proved as a theorem from the other four. Many attempted to find a proof by contradiction, including Ibn el-Haytham, Omar Khayyam, Nasir al-Din al-Tusi, and Giovanni Girolamo Saccheri. The theorems of Ibn el-Haytham, Khayyam and al-Tusi on quadrilaterals, including the Lambert quadrilateral and Saccheri quadrilateral, were the first few theorems of the hyperbolic and the elliptic geometries. These theorems, along with their alternative postulates, such as Playfair's axioms, played an important role in the later development of non-Euclidean geometry. These early attempts at challenging the fifth postulate had a considerable influence on its development among later European geometers, including Witello, Levi Ben Gerson, Alfonso, John Wallis and Saccheri. All of these early attempts made at trying to formulate non-Euclidean geometry, however, provided flawed proofs of the parallel postulate, containing assumptions that were essentially equivalent to the parallel postulate. These early attempts did, however, provide some early properties of the hyperbolic and elliptic geometries. Khayyam, for example, tried to derive it from an equivalent postulate he formulated from the principles of the philosopher. Two convergent straight lines intersect, and it is impossible for two convergent straight lines to diverge in the direction in which they converge. Khayyam then considered the three cases right, obtuse, and acute that the summit angles of a Sarkari quadrilateral can take, and after proving a number of theorems about them, he correctly refuted the obtuse and acute cases based on his postulate, and hence derived the classic postulate of Euclid, which he didn't realize was equivalent to his own postulate. Another example is Al-Tusi's son, Sadr al-Din, who wrote a book on the subject in 1298 based on Al-Tusi's later thoughts, which presented another hypothesis equivalent to the parallel postulate. He essentially revised both the Euclidean system of axioms and postulates and the proofs of many propositions from the elements. His work was published in Rome in 1594 and was studied by European geometers, including Sarkari, who criticized this work as well as that of Wallis. Giordano Vitali, in his book Euclidi Restitua, used the Sarkari quadrilateral to prove that if 3 points are equidistant on the base AB and the summit CD, then AB and CD are everywhere equidistant. In a work titled Euclidis ab omni nivo vindicatus, published in 1733, Sarkari quickly discarded elliptic geometry as a possibility and set to work proving a great number of results in hyperbolic geometry. He finally reached a point where he believed that his results demonstrated the impossibility of hyperbolic geometry. His claim seems to have been based on Euclidean presuppositions, because no logical contradiction was present. In this attempt to prove Euclidean geometry, he instead unintentionally discovered a new viable geometry, but did not realize it. In 1766 Johann Lambert wrote, but did not publish, Theorie der Parallellinien, in which he attempted, as Sarkari did, to prove the fifth postulate. He worked with a figure that today we call a Lambert quadrilateral, a quadrilateral with three right angles. He quickly eliminated the possibility that the fourth angle is obtuse, as had Sarkari and Khayyam, and then proceeded to prove many theorems under the assumption of an acute angle. Unlike Sarkari, he never felt that he had reached a contradiction with this assumption. He had proved the non-Euclidean result that the sum of the angles in a triangle increases as the area of the triangle decreases, and this led him to speculate on the possibility of a model of the acute case on a sphere of imaginary radius. He did not carry this idea any further. At this time it was widely believed that the universe worked according to the principles of Euclidean geometry. Circa 1813, Carl Friedrich Gauss, and independently around 1818, the German professor of law Ferdinand Karl Schweikart had the germinal ideas of non-Euclidean geometry worked out, but neither published any results. Then, around 1830, the Hungarian mathematician János Bolyai and the Russian mathematician Nikolai Ivanovich Lobachevsky separately published treatises on hyperbolic geometry. Consequently, hyperbolic geometry is called Bolyai-Lobachevskian geometry, as both mathematicians, independent of each other, are the basic authors of non-Euclidean geometry. Gauss mentioned to Bolyai's father, when shown the younger Bolyai's work, that he had developed such a geometry several years before, though he did not publish, while Lobachevsky created a non-Euclidean geometry by negating the parallel postulate. Bolyai worked out a geometry where both the Euclidean and the hyperbolic geometry are possible depending on a parameter k. Bolyai ends his work by mentioning that it is not possible to decide through mathematical reasoning alone if the geometry of the physical universe is Euclidean or non-Euclidean. This is a task for the physical sciences. Bernhard Riemann, in a famous lecture in 1854, founded the field of Riemannian geometry, discussing in particular the ideas now called manifolds, Riemannian metric, and curvature. He constructed an infinite family of geometries which are not Euclidean by giving a formula for a family of Riemannian metrics on the unit ball in Euclidean space. The simplest of these is called elliptic geometry, and it is considered to be a non-Euclidean geometry due to its lack of parallel lines. By formulating the geometry in terms of a curvature tensor, Riemann allowed non-Euclidean geometry to be applied to higher dimensions. Terminology: it was Gauss who coined the term non-Euclidean geometry. He was referring to his own work, which today we call hyperbolic geometry. Several modern authors still consider non-Euclidean geometry and hyperbolic geometry to be synonyms. Arthur Cayley noted that distance between points inside a conic could be defined in terms of logarithm and the projective cross-ratio function. The method has become called the Cayley-Klein metric because Felix Klein exploited it to describe the non-Euclidean geometries in articles in 1871 and 73 and later in book form. The Cayley-Klein metrics provided working models of hyperbolic and elliptic metric geometries, as well as Euclidean geometry. Klein is responsible for the terms hyperbolic and elliptic. His influence has led to the current usage of the term non-Euclidean geometry to mean either hyperbolic or elliptic geometry. There are some mathematicians who would extend the list of geometries that should be called non-Euclidean in various ways. Axiomatic basis of non-Euclidean geometry. Euclidean geometry can be axiomatically described in several ways. Unfortunately, Euclid's original system of 5 postulates is not one of these, as his proofs relied on several unstated assumptions which should also have been taken as axioms. Hilbert's system, consisting of 20 axioms, most closely follows the approach of Euclid and provides the justification for all of Euclid's proofs. Other systems, using different sets of undefined terms, obtain the same geometry by different paths. In all approaches, however, there is an axiom which is logically equivalent to Euclid's fifth postulate, the parallel postulate. Hilbert uses the Playfair axiom form, while Birkhoff, for instance, uses the axiom which says that there exists a pair of similar but not congruent triangles in any of these systems. Removal of the one axiom which is equivalent to the parallel postulate, in whatever form it takes, and leaving all the other axioms intact, produces absolute geometry. As the first 28 propositions of Euclid do not require the use of the parallel postulate or anything equivalent to it, they are all true statements in absolute geometry. To obtain a non-Euclidean geometry, the parallel postulate must be replaced by its negation. Negating the Playfair's axiom form, since it is a compound statement, can be done in two ways. Either there will exist more than one line through the point parallel to the given line, or there will exist no lines through the point parallel to the given line. In the first case, replacing the parallel postulate with the statement, in a plane, given a point P and a line not passing through P, there exist two lines through P which do not meet, and keeping all the other axioms, yields hyperbolic geometry. The second case is not dealt with as easily. Simply replacing the parallel postulate with the statement, in a plane, given a point P and a line not passing through P, all the lines through P meet, does not give a consistent set of axioms. This follows since parallel lines exist in absolute geometry, but this statement says that there are no parallel lines. This problem was known to Khayyam, Sakheri and Lambert and was the basis for their rejecting what was known as the obtuse angle case. In order to obtain a consistent set of axioms which includes this axiom about having no parallel lines, some of the other axioms must be tweaked. The adjustments to be made depend upon the axiom system being used. Among others, these tweaks will have the effect of modifying Euclid's second postulate from the statement that line segments can be extended indefinitely to the statement that lines are unbounded. Riemann's elliptic geometry emerges as the most natural geometry satisfying this axiom. Models of non-Euclidean geometry. Two-dimensional Euclidean geometry is modeled by our notion of a flat plane. Elliptic geometry. The simplest model for elliptic geometry is a sphere, where lines are great circles, and points opposite each other are identified. This is also one of the standard models of the real projective plane. The difference is that as a model of elliptic geometry, a metric is introduced permitting the measurement of lengths and angles, while as a model of the projective plane there is no such metric. In the elliptic model, for any given line and a point A, which is not on, all lines through A will intersect. Hyperbolic geometry. Even after the work of Lobachevsky, Gauss, and Beaulier, the question remained, does such a model exist for hyperbolic geometry? The model for hyperbolic geometry was answered by Eugenio Beltrami, in 1868. Who first showed that a surface called the pseudosphere has the appropriate curvature to model a portion of hyperbolic space, and in a second paper in the same year, defined the Klein model, which models the entirety of hyperbolic space, and used this to show that Euclidean geometry and hyperbolic geometry were equiconsistent, so that hyperbolic geometry was logically consistent if and only if Euclidean geometry was in the hyperbolic model, within a two-dimensional plane, for any given line and a point A, which is not on. There are infinitely many lines through A that do not intersect. In these models, the concepts of non-Euclidean geometries are being represented by Euclidean objects in a Euclidean setting. This introduces a perceptual distortion wherein the straight lines of the non-Euclidean geometry are being represented by Euclidean curves which visually bend. This bending is not a property of the non-Euclidean lines, only an artifice of the way they are being represented. Three-dimensional non-Euclidean geometry. In 3 dimensions, there are 8 models of geometries. There are Euclidean, elliptic, and hyperbolic geometries. As in the two-dimensional case, mixed geometries that are partially Euclidean and partially hyperbolic or spherical, twisted versions of the mixed geometries, and one unusual geometry that is completely anisotropic. Uncommon properties. Euclidean and non-Euclidean geometries naturally have many similar properties, namely those which do not depend upon the nature of parallelism. This commonality is the subject of absolute geometry. However, the properties which distinguish one geometry from the others are the ones which have historically received the most attention. Besides the behavior of lines with respect to a common perpendicular, mentioned in the introduction, we also have the following. A Lambert quadrilateral is a quadrilateral which has 3 right angles. The fourth angle of a Lambert quadrilateral is acute if the geometry is hyperbolic, a right angle if the geometry is Euclidean, or obtuse if the geometry is elliptic. Consequently, rectangles exist only in Euclidean geometry. A Sarkari quadrilateral is a quadrilateral which has 2 sides of equal length, both perpendicular to a side called the base. The other 2 angles of a Sarkari quadrilateral are called the summit angles, and they have equal measure. The summit angles of a Sarkari quadrilateral are acute if the geometry is hyperbolic, right angles if the geometry is Euclidean, and obtuse angles if the geometry is elliptic. The sum of the measures of the angles of any triangle is less than 180 degrees if the geometry is hyperbolic, equal to 180 degrees if the geometry is Euclidean, and greater than 180 degrees if the geometry is elliptic. The defect of a triangle is the numerical value. This result may also be stated as the defect of triangles in hyperbolic geometry is positive, the defect of triangles in Euclidean geometry is 0, and the defect of triangles in elliptic geometry is negative. Importance. Before the models of a non-Euclidean plane were presented by Beltrami, Klein, and Poincaré, Euclidean geometry stood unchallenged as the mathematical model of space. Furthermore, since the substance of the subject in synthetic geometry was a chief exhibit of rationality, the Euclidean point of view represented absolute authority. The discovery of the non-Euclidean geometries had a ripple effect which went far beyond the boundaries of mathematics and science. The philosopher Immanuel Kant's treatment of human knowledge had a special role for geometry. It was his prime example of synthetic a priori knowledge, not derived from the senses nor deduced through logic. Our knowledge of space was a truth that we were born with. Unfortunately for Kant, his concept of this unalterably true geometry was Euclidean. Theology was also affected by the change from absolute truth to relative truth in the way that mathematics is related to the world around it. That was a result of this paradigm shift. Non-Euclidean geometry is an example of a scientific revolution in the history of science. Mathematicians and scientists changed the way they viewed their subjects. Some geometers called Lobachevsky the Copernicus of geometry, due to the revolutionary character of his work. The existence of non-Euclidean geometries impacted the intellectual life of Victorian England in many ways, and in particular was one of the leading factors that caused a re-examination of the teaching of geometry based on Euclid's elements. This curriculum issue was hotly debated at the time and was even the subject of a book, Euclid and His Modern Rivals, written by Charles Lutwidge Dodgson, better known as Lewis Carroll, the author of Alice in Wonderland.